Now, unfortunately, regulatory control has got two definitions. The one that we're using here means controlling a controlled variable to some desired set point. The other definition for regulatory control means the opposite of advanced control. And we will not be using that here today, but we will be using it later in the course. Now let's say that in this case we have a constant set point for regulatory control, and it's 80 kilometers per hour. And let's look at what happens when we're driving along. Say we're driving along, and no one is perfect, so there will always be some fluctuations in speed either side of set point. And then we get hit by a gust of wind, and we steady it out, and then we come to a valley, and the speed picks up as we go down the valley, and then we reach the bottom of the valley, and we start climbing up the other side, and then we reach the top again, possibly overshoot a little bit, and carry on. Right? Now the throttle position in response to this will probably look something like that. And going downhill, probably back off the gas quite a long way, and then reach the bottom and give it quite a lot of gas going up the hill, and then there's an overshoot. It'll be something like this. Now we encounter one of the major challenges of measuring regulatory control performance. While we can fairly easily measure the control error, so at every given time there is some control error here, it's easy to measure it, and we can also easily calculate, say, the standard deviation of control error. That doesn't do us much good necessarily, because the problem is that the standard deviation depends entirely on how large the disturbances are, as well as how well the controller is configured and behaving. So measuring regulatory control performance is actually a very complex field. For the purposes of this course, we will be using standard deviation of control error. We'll be looking a little bit at standard deviation of the change in the throttle position. So we can do the same thing, because we don't care about what the actual throttle position is, what the actual manipulated variable value is. It will be whatever it needs to be to control our controlled variable. But we may be interested in rate of change of manipulated variable. Because that, it turns out, can often tell you how badly the manipulated variable is affecting other variables. Okay. Now, one way in which we can measure regulatory control performance fairly easily is with oscillations. Oscillations are almost without exception a bad thing. So what we'll do, there's a number of ways of quantifying them depending on how mathematical you want to get. But what we're going to do is we're going to describe them in ways that make sense to human beings. And so let's say we have an oscillation in our controlled variable, and it doesn't have to be a sinusoid. Frequently they are not sinusoidal, but they'll have a period, which is peak to peak. Sometimes it may be easiest to count several cycles and pick the total duration, and thus calculate an average period. And they'll also have an amplitude. And again, with amplitude, it's possible to, some people are going to be interested in root mean squared and that kind of thing. But really, the physically meaningful one is a peak-to-peak amplitude. And by and large oscillations are bad.